Astronomers have confirmed more than 6,000 planets orbiting other stars. In all that time, searching for years with some of the most sensitive instruments ever built, they have never once confidently confirmed a single moon orbiting any of them. Until now, and the one they just found breaks the naming system before it even gets started. The discovery was published on July 22, 2026, in the journal Nature, led by Kevin Hoy, a student at the European Southern Observatory in Chile, working alongside astrophysicist Alice Zurlo of the Universidad Diego Portales and the Millennium Nucleus of young exoplanets and their moons. The system they were studying is called CD 352722, a young star located about 73 light-years from Earth in the constellation Columba. That star has roughly half the mass of our Sun, which already makes it smaller and dimmer than the star at the center of our own solar system. Orbiting that star is an object called CD 352722b, first directly imaged back in 2011. It's a brown dwarf, sometimes nicknamed a failed star, because it formed the same way stars do, out of a collapsing cloud of gas, but never gathered enough mass to ignite sustained hydrogen fusion at its core. Brown dwarfs sit in an awkward middle zone, too massive to be called a planet, but too small to actually shine like a star. This particular one weighs in at around 37 times the mass of Jupiter. Here's where it gets strange. The team wasn't trying to find a planet, and they definitely weren't expecting to find a moon. They were using an instrument called CRIERS Plus, mounted on the European Southern Observatory's Very Large Telescope in Chile, to apply a technique called the radial velocity method to that brown dwarf. Radial velocity is one of the oldest tricks in the exoplanet hunting toolkit. It's the exact same method that was used back in 1995 to confirm 51 Pegasi b, the first planet ever discovered around a sun-like star. Instead of looking directly for a planet, you watch for the tiny gravitational wobble that an orbiting object causes in whatever it's circling. If something invisible is tugging on an object rhythmically, on a predictable schedule, that's usually a sign there's a companion nearby. Nobody had ever tried pointing that specific technique at a directly imaged brown dwarf before, mostly because nobody expected there to be anything worth finding there. Between October of 2023 and February of 2026, Hoy's team tracked subtle, repeating shifts in the brown dwarf's motion. The pattern that emerged pointed to something orbiting it every 170 days, with a mass of at least about 90% of Jupiter's, big enough on its own to easily qualify as a planet by any normal definition. Except this object doesn't orbit a star. It orbits a brown dwarf, which itself orbits the star. And that's where the entire naming system starts to break down. In our own solar system, definitions are simple because the categories are clean. Stars are stars, planets orbit stars, and moons orbit planets. Astronomers already had a working term for something that orbits a planet outside our solar system, an exomoon. But nobody had ever needed a term for something that orbits a brown dwarf instead, because nothing like this had ever been detected with any real confidence before. Kevin Hoy has been blunt about the awkwardness of it. According to Hoy, the newly found object is clearly massive enough to qualify as a planet in its own right, yet it doesn't orbit a star directly. It orbits an object that orbits a star, making it something like a third-generation companion in the system. Being that third wheel, as Hoy put it, is part of what makes people want to call it a moon in the first place, even though it looks nothing like the small, rocky moons orbiting planets in our own solar system. Alice Zerlo, one of the study's co-authors, has pointed out just how differently language breaks down once you leave our own solar system behind. In our system, she explained, the line between star, planet, and moon is obvious because the categories were built around exactly the objects we already have names for. In the CD 352722 system, those same lines blur together, and the whole business of naming things gets a lot more complicated. It's less that scientists pick the wrong words, and more that nature simply doesn't organize itself around the tidy categories humans built to describe one specific, ordinary-looking solar system. To be clear about how solid this detection actually is, the team describes it in their own words as plausible, the strongest evidence yet for an exomoon-type object, not a fully confirmed closed case. That distinction matters because this isn't the first time astronomers have proposed a candidate exomoon. Two previous candidates, known as Kepler 1625bi and Kepler 1708bi, were proposed in 2018 and 2022 respectively, and both remain contested within the astronomical community to this day, never reaching the kind of confirmation that would let scientists stop debating them. The CD 352722 detection is being treated as more convincing than either of those earlier candidates, mostly because the radial velocity signal lines up cleanly with the models the team built to predict what an orbiting companion should look like. But more convincing is still not the same thing as certain, and further observations will be needed before anyone calls this case fully closed. There's a bigger reason this detection matters beyond just this one strange little system, though. Every previous exomoon search focused specifically on planets, looking for the faint gravitational or transit signatures a moon might leave behind while orbiting a confirmed exoplanet. Nobody had systematically tried applying radial velocity analysis to directly image brown dwarf companions instead. Now that this approach has actually worked once, every brown dwarf companion astronomers have already directly imaged and can get a clean, high-resolution infrared spectrum from effectively becomes a brand new candidate target for the exact same search. In other words, the real discovery here isn't just one strange orbiting object, it's a whole new hunting ground that didn't exist as a serious option before this study came out. Brown dwarfs themselves are already a strange enough category on their own, long before this detection ever came along. Depending on how you define the boundary, they generally range from about 13 to 80 times the mass of Jupiter, heavy enough that gravity briefly triggers some nuclear reactions in a young brown dwarf, but never quite enough to sustain the same stable hydrogen fusion that keeps a true star burning for billions of years. Instead, brown dwarfs spend their entire existence slowly cooling off, radiating away whatever heat they were born with, fading dimmer and dimmer over billions of years without ever properly igniting. That's part of why CD 352722b was so hard to characterize in the first place, even though it had already been directly imaged back in 2011. A dim, cooling object like that doesn't behave like a star in any of the ways astronomers are used to modeling, which makes searching for anything orbiting it a fundamentally different problem than searching for a planet around an ordinary star. It also fits into a much older, recurring pattern in astronomy. Every time researchers assume a distant star system should roughly resemble our own, nature tends to prove that assumption wrong. Our solar system has a tidy hierarchy. One star, several planets. Some of those planets have moons, and the categories never blur into each other. CD 352722 doesn't respect any of that structure. It has a star roughly half the mass of the Sun, a brown dwarf standing in for where a planet might normally be, and now orbiting that brown dwarf, An object that's massive enough to be a planet, but doesn't circle a star at all. Nobody is rewriting the textbook definition of moon based on one debated detection in one distant, unusual system. But the fact that this kind of object can exist at all, massive, planet-sized, orbiting something that is itself neither a planet nor a star, means the neat categories built around our own solar system were never guaranteed to describe the rest of the galaxy. The universe, once again, turns out to be far less interested in fitting inside the tidy boxes we built for it, long before we ever had the tools to look this closely. Beyond what you can see, but never beyond what you can understand. Subscribe and check out the rest of the channel. New episodes on space, physics, and the edges of what we understand, with new content going up every day.